Good morning, everyone. Welcome to the, second session of the day. This is Foundations 2. I'm Isa. I'm going to be chairing. Yeah, and so let's get started. Our first talk today is going to be by Kaija, who's going to be telling us about a novel commitment construction framework.
Thanks for introduction. It's my honor to be here to talk about our paper, Anonymize and Extract a Novel Commitment Construction Framework based on loop actions. It's a joint work with 安宇完、恒一罗、吴肖流、谭安、叶明潘 and 肖云文. Okay. Let's review the loop action. Let's G mean loop, X mean set. And start will map from G times X to X. And such triple in the loop action if start is compatible with the loop operation. And we need some notations. For any X, OX is defined as the orbit of X, and stable X is defined as the stabilizer of X. And for IXY, it's defined as the loop element that maps X to Y, and it's a coset of stable X. And we need some cryptography properties. Firstly, we need one-wayness, which means the loop action, it's hard to invert the loop action. And secondly, we need pseudo-random, which corresponds to distinguish orbit problem, which means the uniform distribution of different orbits are computationally indistinguishable. And finally, we need a collision resistance, which corresponds to search stabilizer problem, which means you cannot find a non-trivial loop element in stable X. Okay, next we review the commitment scheme. First, the G algorithms generates the public commitment key CK. And for sender, he first use CK to commit the message M and output the commitment value C and opening value E, and sends the commitment value to the receiver. And in open phase, he sends the opening value E to receiver, and the receiver use C and E to compute the message M. So for security, it needs to satisfy hiding and bending. For bending, it means the sender cannot open the same commitment value to different message M and M prime. And for hiding, the commitment value does not disclose any information about message M. Okay, and our work focuses on constructing commitment based on loop actions. Firstly, we propose the two key techniques for loop actions, the randomization and the randomness extractors. And we use these two techniques to obtain a novel framework to construct various commitments based on loop actions, including basic commitments, new model commitment, and enhanced linkable commitment. And we actuate all our proposed commitments using lattice isomorphism problem and lattice automorphism problem. And finally, we use LIP to provide a repair and improvement to the non-interactive commitment proposed by Alcano, Falamini, and Kankami. Okay. And for related work, there are so many commitment schemes based on loop actions, such as meet commitment from loop action, and new model commitment from a median loop action, and linkable commitment from loop action. Okay. And firstly, I introduce the two techniques. For the randomized algorithm, which means for loop action, and an anonymized algorithm R takes as an input and outputs G star X and G according to a distribution denoted as Rx, such that for any x and x prime in the same orbit, the marginal distribution of the first variable are identical for Rx and Rx prime, and G is uniformly distributed on such coset if x prime prime and G are from the distribution Rx. Okay, and for deterministic extractor, which means for loop action with the distribution and M is a finite loop, a deterministic extractor is an efficient algorithm E that maps G to M, such that for any Hx from the distribution and y prime in Ox, it holds that Eg is uniformly distributed on M, just as shown in the right picture. The red point indicates the loop element that maps X to Y, and the blue point indicates the loop element in M. So if G is uniformly distributed on such coset, Eg will be uniformly distributed on M. Okay, and now we can construct a basic commitment. Firstly, we sample the Hx from the distribution and output the H star X equal to Y as the probabilic commitment PCK. And for the sender, he first randomizes Y and outputs Y prime and G. And next, he computes the commitment value equal to Eg times M and Y prime. And for opening value, it will be the loop element that maps Y to Y prime. Okay. And for the receiver, she first verifies the E star Y equal to C2, which is Y prime. Okay, and if it is correct, she computes the message in such a way. Okay, and for security, this commitment scheme is perfectly hiding and computationally binding based on search stabilizer problem. Okay, next we introduce the local constant extractor, which is defined with two distributions. And for distribution E, the behavior of local constant extractor are the same as the deterministic are the same as the deterministic extractor. But for distribution E prime, the behavior is different, which means for Y and Y prime in Ox, it holds that Eg is a constant on M, just as shown in the picture. Now, the distribution E prime is such distribution, and if G prime is from such coset, Eg prime will be a constant on M. Okay, so we can transform the basic commitment 1 to basic commitment 2 by replacing the deterministic extractor with local constant extractor, and CK from distribution E to CK from the distribution E prime. So the basic commitment 1 is perfectly hiding based on search stabilizer problem, and commitment 2 is perfectly bending based on distinguished orbits problem. Okay, and next we introduce a new commitment primitive, enhanced linkable commitment. In this paper, the authors introduced a linkable commitment, which allows a sender to provide a short proof to prove two commitments have the same message without revealing it. And we know the homomorphic commitment satisfies such homomorphic operation. Okay, and which enables one to prove the value of M1 times M2's inverse without revealing any additional information. So we propose the enhanced linkable commitment. It can provide a short proof for two commitments, and proving the value of M1 times M2's inverse without revealing any additional information. So the enhanced linkable commitment is stronger than linkable commitment, but weaker than homomorphic commitment. So to obtain an enhanced linkable commitment, we just need to replace the deterministic or local constant extractor in basic commitment with the following homomorphic extractor, which means we need E to be a surjective loop homomorphism. So the short proof for two commitment will be the loop element that maps Y1 to Y2. And so that we can prove the message we can prove the value of M2's inverse times M1 by such a way. Okay, and for security, it can be based on search stabilizer problem or distinguish orbit problem. And furthermore, if we replace the local constant extractor in basic commitment 2 with the following trapdoor extractor, we can obtain a new model commitment. And for security, it can be based on distinguish orbits problem. Okay, next we introduce some lattice assumption. Firstly, the lattice isomorphism problem, which means given two quadratic forms Q1 and Q2 associated with lattice L1 and L2. And you need to find a unimodular matrix U such that U times Q1 times U transpose equal to Q2. And for lattice automorphism problem, which means given a quadratic form Q associated with a lattice L, and you need to find a unimodular matrix U such that U is non-trivial and U times Q times U transpose equal to Q itself. So furthermore, we can describe lattice iso using loop action. We need Q to be a quadratic form, and G be such loop, and X be such set. And loop action on such triple can be defined as follows, which is a loop action. So next we show some instantiation with LIP or LAP. Firstly, for the randomized algorithm, it arises from the random self-reduction of lattice isomorphism problem. So we can use the paper by Lucas and Van Warden to instantiate it. And for deterministic extractor, it's more complexity. First, we require the Q be a quadratic form of an n-dimensional lattice, where n is even and the lattice satisfies such a condition. Okay. So for the loop action, we can define the distribution as follows. And if we let M be such a loop, it can be proven that the determinant will be a deterministic extractor. And for other instantiation, you can see paper for more details. Finally, we show some open questions for future work. Firstly, explore the alternative assumptions for instantiation, such as code equivalence or isogeny, will be an interesting question. And it will be interesting to utilize the randomization and extractor to construct other primitives. And finally, how to construct a homomorphic commitment based on general loop action will be a really interesting question. Okay, thank you for your attention.
Do we have any questions for the speaker? We have a lot of extra time. Because if not, I'm not going to ask any questions, so this is your opportunity.
Maybe a stupid question. So, where is the random extractor employed in your scheme?
Okay. Random extractor. Wait a moment. Yeah, here. We use the random extractor in here to hide in the message. Yeah, so it's used here. Okay.
Hello? Okay. Yeah, okay, cool. So everyone, we can thank the speaker again. This is Kaija.
Thank you.
Should I wait?
Oh yeah, so we have like a couple minutes until, I guess, we can just like wait a couple minutes. You can all stare at her.
I can wait. Yeah, I'm fine. With both.
Oh yeah, no, I was supposed to ask you like deeply personal question, but you have the hot mic. Okay, cool. Yeah, let's get started. So our next talk is going to be by Shani on instance compression. Take it away.
Thank you, Isa, for the introduction. So hi, everyone. I'm Shani Ben David, and I'm going to talk about our paper, Instance Compression Revisited. This is a joint work with Gal Arnon and Eilon Yogev. So collision-resistant hash functions are extremely powerful and widely used in cryptography. And one of the major open problems in cryptography is, can we construct collision-resistant hash functions from the minimal assumptions that one-wave function exists? So in this talk, we're going to talk about the path for achieving this goal. So another way to frame this question is through Impagliazzo's 5 words. So Impagliazzo described 5 hypothetical words. Each one of them corresponds to a different cryptographic or complexity assumption. And specifically, in Minicrypt, we assume that we have only one-wave functions. And the question is, if the real world is Minicrypt, do we have collision-resistant hash functions? So despite of decades of research, we are not aware of any construction for CRH from one-wave functions. And in fact, we have strong barriers indicating that such a construction will require non-black box techniques. So the first barrier introduced by Simons at 1998, showing that any collision-resistant hash function from one-wave function will require non-black box techniques, so we cannot achieve it using only black box techniques. And later on, Asherov and Segev generalized these results and proved that even if we have the strong assumption of indistinguishability obfuscation, we still cannot construct collision-resistant hash function from one-wave function using only black box techniques. Now, one promising path towards bypassing those barriers was introduced by Harnik and Naor and used an object called instance compression. And now we're going to define instance compression. So instance compression for an NP language is an efficient algorithm that takes an instance, x, and compresses it to a small instance, x prime. And what we want from this algorithm is to preserve the information about the language. So if we start, for completeness, if we start with instance x that is in L, we want x prime, the compressed instance, to be in L prime. And if we start with, for soundness, we say that if we start with x that is not in the language, we want to get x prime that is not in L prime. So what we actually want from this algorithm is, without knowing how to decide the language, to compress the instance and preserve the correctness of the instance. So the IC algorithm essentially generates a mapping between instances in the language L to instances in L prime, and from instances that are not in L to instances that are not in L prime. Now, for the compression parameter, we want the compressed instance x prime to be of size that is polynomial in the witness size of the language L. So we do not expect to have something that is sublinear in the witness size, as this would contradict the ETH assumption. But for some languages, some relations in which the instance is huge and the witness is small, this definition, this notion is strong. So what Harnik and al. Actually proved is that, assuming this instance compression object, we can get from one-way function to CRH using non-black box techniques. So they had this star object, the instance compression object, that can transform them from one-way function to collision-resistant hash function. And the question is, do we have this object? Can we get it from one-way function? For this question, Fortnau and Santanam showed that, assuming instance compression for NP, then polynomial hierarchy collapses. So we do not expect to have instance compression for NP. And this path, at this point, was closed. And so we don't have IC for NP, and we're interested of reopening this path by finding the right notion of IC, finding a weaker notion that it's both strong enough for achieving CRH and exists under cryptographic assumptions. So the focus is to find the right notion. The first weakening that we have been thinking about is having computational soundness. So let's define computational instance compression. In this case, we have an algorithm, an instance compression algorithm, efficient algorithm, that now depends on some CRS. This is now it's a cryptographic primitive that is initiated by a CRS. And again, for completeness, we want perfect completeness. We want that if the original instance was in the language, then x prime, the compressed instance, is going to be in L prime. And for soundness, we want strong computational soundness. We want that it will be computationally hard to find an instance that is not in the language and mapped to a new instance, x prime, that is in L prime. So you can see in the red arrow here that it might be that there are wrong mappings for instances that are not in the language to instances in L prime, but it is going to be computationally hard to find them. The question is, first of all, is this enough for constructing CRH, and do we have this from cryptographic assumptions? So for this question, so first of all, this object is enough, but we do not expect to have this object under standard assumptions. So if there exists CAC with strong soundness, polynomial hierarchy again collapses. So we do not expect to have this object. And now we're going to define the weaker notion introduced by Bornstein and Rothblum. So in fact, Bornstein and Rothblum were the first to define computational instance compression. And the way they defined it is with another algorithm called witness transformation. So in their notion, they had two efficient algorithms, instance compression and witness transformation. Again, this is a cryptographic primitive that depends on a CRS. And again, now we're going to talk about transforming from a relation R to relation R prime rather than just from a language to language L prime. The instance compression again compresses the instance, but now we have the additional algorithm, witness transformation, that gets as inputs x and w, and generates new instant w prime to x prime, to the new compressed instance x prime. So for completeness, we want something stronger. If we have x and w that are in the relation R, then x prime and w prime that was efficiently generated are going to be in R prime. For soundness, they define non-adaptive computational soundness that says that for any fixed x that is not in the language, it is going to be hard to find a witness w prime for that instance x prime. So it is going to be hard to find a valid witness to the new compressed instance. In this non-adaptive notion, the adversary gets to pick x independently of the CRS, and then after that, it can see the CRS and find w prime. The compression parameter will stay the same through the entire talk, and now what happens is that it might be that the adversary can find an instance that is not in L and is mapped to instance in L prime, but it is going to be hard to find a valid witness W prime for that instance, so the task of the adversary is harder. It needs to find both an instance and a witness. And nicely, they constructed non-adaptive CAC from standard assumptions. The problem is that this object does not seem to suffice for constructing collision-resistant hash functions. So this notion seems to be weaker than what we need. And let's zoom out for a second and see what we have until now. So we have two notions of instance compression, one that is statistical, one that is computational. Both of them are not likely to exist, but would have been enough for constructing collision-resistant hash function. And we have another object called non-adaptive CAC that Bronfman and Rothblum constructed using standard assumption. And in fact, they used, on the way they went through another object called succinct PCA, they went through the non-adaptive version of this object, and using this object achieved non-adaptive CAC. And the big question is, do we have something here in the middle that will both be enough for constructing collision-resistant hash function and exist under standard assumption? For that, we defined adaptive CAC. So first, let's look again at the non-adaptive CAC definition. So before we said that in the non-adaptive computational soundness, the adversary gets to pick X, the instance, before seeing the CRS. And now in the adaptive setting, we allow the adversary to choose both the instance and the witness W prime, giving the CRS. And now that we have a stronger soundness notion, we ask the question, can we construct this object under standard assumption? And again, is this enough for constructing CRH? For these questions, we answer with our second theorem, saying that assuming adaptive CAC, we can get CRH from one-wave function, and this construction is actually non-black box. The same construction worked for Harnik and Naor works in this case. Most of the work is the analysis. And we also show that we can get adaptive CAC from standard assumptions. So it seems like we have the right notion. It's strong enough for CRH and follows some standard assumptions. And let's look at the big picture again. So how can we get adaptive CAC? In previous work, we constructed adaptive succinct PCA. And from this object, we show, from standard assumptions, from this object, we show how to move to adaptive CAC. And we actually prove in our theorem, our second theorem, another thing. We show that collision-resistant hash function implies adaptive CAC. So this is a strong indication that to get from one-wave function to collision-resistant hash function, we need to go through adaptive CAC. Now, another way to get adaptive CAC is through I/O. So recent line of work showed that assuming I/O plus some structured assumption, we can get snarg. If we look into their construction, this snarg is actually pre-processing snarg. And what we show in our paper is that pre-processing snarg is enough for, it implies adaptive CAC. So to bypass the impossibility result of Asherov and Segev, we need to kind of get rid of the additional structured assumption here and go from I/O to collision-resistant hash function. And using I/O, also recent light of work shows that using I/O we can get snarg, but this snarg is not essentially preprocessing snarg and therefore doesn't seem to be enough for adaptive CAC. So the big question left from this up until here is, can we get one-way function, maybe plus IO, from one-way function maybe plus IO to adaptive CAC, and this will complete the proof from one-way function to collision-resistant hash function. Now, this construction might be black box, as our second theorem is non-black box, uses non-black box techniques. And this is the main open problem remains in the paper. Now, zooming out from the conversation about collision-resistant hash function, we kind of got greedy there and asked the question, do we have something else in the middle? Can we get something stronger that maybe we can use to achieve other results? So looking at the Harnik and Orr results, they also proved that if they had instance compression plus additional property called witness retrieval, they can get from one-way function to public encryption. So we don't have instance compression, so of course we don't have the stronger notion of instance compression, but can we achieve the computational version, like the CAC plus, with witness retrieval? Okay, so let's define CIC with witness retrieval. So here we have, again, two algorithms, two efficient algorithms, instance compression and witness retrieval. And the witness retrieval needs to generate the witness, but now given only the compressed instance x prime and the original witness w2x. So now the witness retrieval algorithm has less information, and it has to do the same work as the witness transformation algorithm that we saw before. And the question is, do we have this algorithm? Okay, so for this question, do we have this notion? So for this question, we answer with our third theorem, saying that assuming public encryption plus NIZK, we don't have CIC with witness retrieval, not in the adaptive and not in the non-adaptive setting. So a few words about this proof, just some intuition. So what we show, actually, is we go through another object called incompressible public encryption. And intuitively, this object means that we cannot take the ciphertext and compress it efficiently and yet preserve the information about the underlying message. And the CIC intuitively says that we can compress some instance and preserve the information. So those objects kind of contradict each other. So the CIC is used as an adversary to the incompressible public encryption scheme. Okay, so let's summarize what we have until now. So we have new definition for CIC. We use it to construct collision-resistant hash function from one-way function. And we do not expect to have other stronger CIC notions. And the big open question in the paper is, can we construct adaptive CIC from one-way functions, which will eventually lead us to construction from one-way function to collision-resistant hash function? And that's it. This is our path from one-way function to CRH, and thank you so much for listening.
Wow, we have another speedy talk. Lots of times for questions. So does anybody want to? Okay.
What are the standard assumptions?
What, sorry?
That you can use to build adaptive CIC, what are the assumptions?
So one of them is LWE, one is bilinear maps. So we go through the adaptive PCA, and in the PCA paper, we use those assumptions. I think there is another one, but I don't currently remember.
Okay, thank you.
All of the assumptions are we can construct CRHs.
Sure,
yeah.
it's not
otherwise,
surprising,
yeah.
Just one other so, and how close are you to showing that like snogs plus one-way functions imply CRHs? So you mentioned for pre-processing snogs you can get that, but
how can I use
this? Yeah, so pre-processing snogs plus one-way functions imply CRHs. That's one of your results, right?
Yeah.
So what is why doesn't that apply to like non-pre-processing
For
snogs?
snug, yeah. So actually the transformation is quite easy. So pre-processing snarg, the verifier kind of has an offline stage before seeing the proof, right? You have the instance, and it preserves some small state, right? And then after that, he can see the witness and verify everything using the compressed state. So the state is the compressed instance. This is really easy. So this is the state is a compressed instance, and the witness is the proof. Okay. So and just for regular snark, you don't have the pre-processing stage. And using a CRH, you could have from snark to pre-processing snark, but I cannot use CRH, right? So yeah.
Nick just asked my question, so.
Oh, amazing.
But thanks for the talk.
Thank you.
Cool. Do we have anybody else who has anything? Any pressing questions? You?
You mentioned that non-adaptive doesn't seem to imply collision resistant. Can
Yeah.
you elaborate why you don't know? You didn't prove that.
So why? So I can talk about the intuition. I didn't prove that it cannot. It's not enough. Maybe we can just use one-way function and then get CR8, right? So drop everything in the middle. But the intuition is that when we are constructing the CRH, you have the hash key, right? The hash key includes the CRS. Now the adversary that attacked the CRH, the hash function, can see the CRS and then choose, and then pick the instance. So we essentially need an adaptive notion from the security guarantee that we need to achieve for the CRH. This is very intuitive, I think. Yeah. Okay. So.
Okay, yes, there's like time for one more, but if we're all good, then we can thank Shani again.
What's up, man?
Yeah, and so our last talk of the session is actually going to be remote. Rachid is going to be joining us from very early in the morning, East Coast US. So thank you for being awake.
Yeah. Shall I speak? Can everybody hear me? Yes. Okay. So hi everyone, I'm Rachid and I'm awake and I'm going to talk about succinct randomized encodings from laconic function evaluation. And this is joint work with Nir Bitansky at NYU. Let's begin with what is a randomized encoding. So a randomized encoding is an object where if you have a complex function f and an input x, and you wish to compute f of x. So this encode algorithm takes f and x and outputs f tilde of x. But this encode algorithm should not just run the function f on the input. So because this function f is complex, we want the encode algorithm to be simpler than just running the function f itself. And we have certain properties that we want from f tilde of x. We want it to be useful, so we want correctness, which means given f tilde of x, there is a decode algorithm that can compute f of x. Security means that f tilde of x should not leak any information about f or x other than f of x. So what do I mean by this complex computation into a simpler one? For this talk, we'll focus on succinct randomized encodings, where we can think of a function f as a program M or a Turing machine M that runs on input x for t steps. So the encode functionality that I want is that the time to run this encode function is much less than time t. And even though this is much less than time t, m tilde of x it can still be used to compute m of x once we decode it. So the decode will involve much of the complex functionality of running the Turing machine M on x, but I still want this strong functionality. So this is a cool object, and it has a lot of applications. So imagine that you're a client who wants to compute some machine learning algorithm that is taking like hundreds of years to run, and you want to outsource this to a server. So you can do this by running a succinct randomized encoding and giving that succinct randomized encoding to the server. So now the server can do all the complex computation, and your input X is still, or the machine learning data that you're running on is still, you still have privacy on the data. It has applications to MPC and to getting advanced forms of encryption. But the application that I want to focus on is an application of time lock puzzles. So what are time lock puzzles? Time lock puzzles are an object where you can encode a message M and lock it for a certain period of time. So there are two key properties of a time lock puzzle. First is that the time to generate this puzzle should be very efficient. And the second is that once you've generated this time lock puzzle, nobody, even a powerful supercomputer, cannot open this up in much faster than time t. So this is a great object, and it has a lot of applications to sealed bid auctions, non-malleable commitments, blockchain front-running prevention, fair contract signing, cryptocurrency payments, and more. So if you want to think of one such application, let's say sealed bid auctions. So everybody who is participating in the auction can time lock their bids and submit it to some public bulletin board. And you're locking it for the entire phase of the bidding phase. So nobody can, during the bidding phase, can figure out what the bid is. But after the bidding phase ends, everybody can open up each of the bids and figure out who won the election or who won the auction. Similarly, this can be used in preventing blockchain front running, where you can time lock blockchain transactions and more of these applications. Okay, so hopefully I've convinced you that this primitive is very useful. And let me focus on our results on constructing this primitive. So we give a new construction of a succinct randomized encoding where the encode time can be made as small as we like. So what do I mean? So give me a constant, let's say 0.001. And the encode time for this succinct randomized encoding can be t to the power 0.001. We gave a generic transformation which shows that if you have any laconic function evaluation scheme with some natural efficiency preservation property, which I'll explain during the talk, then you can construct this succinct randomized encoding. And along the way, we conceptually simplify some of the contributions from a prior work. So what is the prior work that I'm mentioning? So imagine you have a Turing machine M, which runs on some input X, and it takes time T and space S to run this Turing. When this Turing machine runs on this input X, it takes up space S. From indistinguishability obfuscation, we have a construction where the encode time can be made independent of this T and S. But the only well-studied assumptions that we have to build I/O involve bilinear maps, and they're not post-quantum secure. And in general, in cryptography, we want to diversify the assumptions that we can build different primitives from. So in a recent breakthrough work, Agrawal, Malavolta, and Zhang showed how to do this from the circular secure learning with errors assumption. And this is conjectured post-quantum secure. And if you're familiar with FHE, it's a similar assumption as FHE. But they were only able to get the encode time down to square root of t and had some space dependence. So the encode time for them was square root t times space s times poly lambda. In our work, we get this down to any constant. So t to the epsilon times s times poly lambda. And the assumption is the same, the circular secure learning with errors. Okay, so let me briefly explain what is this object laconic function evaluation. And I'm going to be using a simplification of it for our purposes. So imagine there's some function f, which you want to compute on your on some input x on. So there is going to be a setup phase, which is going to output a public key. The input x seeing this public key can encrypt and output a ciphertext CT. The ciphertext CT can, just looking at this public key and this function f, can decrypt back to f of x. So we need some efficiency properties on these public key for this notion to become non-trivial. What are the efficiency properties that we need? Even though it takes time dependent on the size of the function f to compute this public key, the size of this public key is very short. So Cecile, Lin, and Luo in 2023, in a wonderful result, showed how to use circular secure LWE to build such a laconic function evaluation scheme, where public key size is only dependent on the input plus output times poly lambda. So if the function is going from n bits to m bits, the size of this public key is n plus m times poly lambda. And this involved like a lot of years of work where we initially knew only how to do it from input plus output and some circuit depth dependence of this function. But now we can get this from this notion where we only have input plus output times poly lambda. So we'll be using this laconic function evaluation scheme for a final construction. Okay, let's jump down to the final construction. And security is similar to randomized encoding, where the ciphertext should only reveal f of x. So Agrawal, Malavalta, and Zhang showed that this kind of an LFE object is already good enough to doing succinct randomized encoding in some pre-processing setting. So what do I mean by pre-processing setting? The setup can take the Turing machine M and some time t and output this public key in some large amount of time. So it can take times t times s times poly lambda to generate this public key. But once this public key is generated, this public key, because it's short, it only depends on s times poly lambda. You can actually make the encryption algorithm. So the encryption algorithm only takes public key and input x. So x is s bits long, and public key is s times poly lambda bits long. So this encryption algorithm is actually efficient. So this gives you a succinct randomized encoding in this pre-processing setting. But we want to make it more useful than just the pre-processing setting. So Agrawal, Malavalta, and Zhang had a contribution where they just envisioned dividing this Turing machine computation in square root t steps. So think of the circuit Cm square root t performing square root t steps of the Turing machine on space S. So they do the natural thing. They run this through the laconic function evaluation procedure and output this public key. It takes times square root t times s times poly lambda and outputs the size s times poly lambda scheme. But notice now that if you just encrypt your ciphertext under this laconic function evaluation scheme, now when you decrypt it, you'll know the state after square root t many steps. And this is undesirable. So remember that the notion of security that we only want to reveal information at the end of t steps. So if we reveal information at some intermediate point, that's going to violate security. So one natural way to fix this is, let's say I throw encryption in there. So instead of the circuit, I now have a symmetric key encryption with the circuit. So now it's going to output a symmetric key encryption of the state. And now we're happy for security. But we still want functionality to go through. So the way I'll make the functionality go through is, I imagine there's some gadget matrix G, gadget circuit G, which has the secret key for the symmetric key encryption encoded in there. So what does this G do? It decrypts the symmetric key and outputs an encryption of the LFE. So now that I have an encryption of an LFE on state of square root t, I can rerun this whole LFE decryption procedure to get an encryption under state of 2 times square root t steps. And I can go and make this move forward. So let me explain this. So there's this LFE algorithm, which is performing square root t many steps. And then there's this gadget object, which is decrypting and output LFE encryption. My succinct randomized encoding will look like this. It will consider the first ciphertext and square root t many such gadgets. What will a decryptor do? It will perform LFE decryption to get the secret key encryption under key K1. Then it runs the gadget and gets this encryption under this of the state at square root t many steps. I run my LFE decryption again to get a secret key encryption under key K2, which I can use the gadget to get encryption under LFE encryption of 2 times square root t, and so on. In the end, I can get the output, which is m of x, or the evaluation of the circuit M at t steps. And note that this is kind of nice because now the time to generate this only depends on square root t times the time to generate all of these gadgets, plus the time to generate one ciphertext, which we've already seen is short because the public key size is short, and the time to generate this public key, which I already mentioned, is square root t times s times poly lambda. So we're getting closer. And similarly, the sizes are also square root t times the gadget plus the ciphertext plus the public key. So what is this gadget? This gadget in our construction will just be a gobbled circuit. What is a gobbled circuit? So given a circuit C and some input X, the circuit C is mapping from S to L bits, and the input X is on S bits. There are two algorithms, then an input encryption algorithm and a circuit encryption algorithm. The input encryption algorithm takes some symmetric key K and encodes the input from X to tilde of X. This is called the gobble input. Similarly, the circuit encryption algorithm will take the symmetric key, same key K, and output a gobbled circuit of C, which I'll denote by G of K. Correctness says that there is an evaluation algorithm that takes in X tilde and G of K and evaluates to C of X. The key property that we want in our scheme is, notice that because the input encryption algorithm only takes in X and K, which is some lambda many bits, this input encryption algorithm only takes time S times poly lambda to compute this gobbled input. And more crucially, this is independent of the output of the computation or the circuit. So it does not depend on L, which is the output of the circuit, and it does not depend on C. Contrast this with LFE, where the public key did depend on the input plus output behavior, and thus the encryption algorithm does depend on input plus output. So how do I use this object? So recall that the circuit that I wanted to gobble was the LFE encryption circuit. So this is the circuit that I'll gobble. It takes an X and outputs an LFE encryption. The LFE would just be running this circuit square root, the Turing machine square root t many steps, and outputting an input encoding under the same secret key K. So how long does it take to generate this public key? It takes square root t times s, because that's how much computation it takes to run this Turing machine for square root t many steps, plus this time to generate this input encoding. And similarly for size. And now notice that if this input encryption somehow started to depend on the circuit or the output of the circuit, then you would have a circularity, because this public key depends on the input encryption. And this input encryption, if it depended on the circuit, then it would depend on the LFE encryption algorithm, which decides what the public key is. So there is a kind of circularity happening here, which we want to sort of make it independent. And gobbled circuits are the right tool to do this. Agrawal, Malavalta, and Zhang also did this, but they used more algebraic tricks and hint fully homomorphic encryption to do this. And we simplified some of their template and made all of this more simpler by just observing that you can use gobbled circuits to do this. So this is our final construction. You have the LFE set up, and you have these gobbled circuit. You have square root t many of these gobbled circuit. The time to generate them is just s times poly lambda, because that's how big these gobbled circuits are. And this gives you at least square root t many computation. How do I get to t to the epsilon from square root t? One basic strategy is just rerun the computation again. So you already have something which is square root t times s. What if I run a succinct randomized encoding over this computation again? If I do such this trivially, then I do get t to the 1/4, because I have a square root dependence on the time. But there is a space multiplication as well. So I'll get the square root dependence on the time, so t to the 1/4 dependence on time. But because of the space, I will again see the square root t show up. So now the time to do this computation will be t to the 3/4. And we've made no progress here. So our main observation here is to actually go beyond square root. Notice that LFE is sort of asymmetric. Even though it takes a lot of time to compute, it outputs something very, very short. So can we use this asymmetry? So what do I mean? Using this asymmetry, let me divide the Turing machine steps to take more time to do the Turing machine computation. So let's say it takes t to the 2/3 to do the Turing machine steps. how many gadgets now will I have to output? I'll only have to output t to the 1/3 many gadgets. And I'll do the same LFE encryption, but now the time is t to the 2/3. But now if I bootstrap this or run another succinct randomized encoding, which takes square root t many steps here, then I have achieved something non-trivial. Now I have time, which takes 1/3. And it takes a little bit more steps where space, where you've grown the space by some factor. But now you've at least made a computed a succinct randomized encoding, which takes time t to the 1/3. So you made non-trivial progress if you do this. There is a slight caveat that you can only do this if the setup algorithm is space efficient. So I've told you that the public key size is short, but what if the way the setup was being computed, you somehow blow up the space while you're doing these intermediate computation and then shrink it again? If such a thing were to happen, then you would take that hit in the space. We don't want such a thing to happen. So I need to sort of convince you that the setup is actually a space-efficient algorithm. And this is the efficiency property I talked about. And a slight caveat here, the way I've shown it, you take a hit in space, but in the paper we show how to even improve the space. So just a quick, because I only have a few minutes. This LFE setup is space preserving, because I can think of a circuit C, which takes this input inside this LFE algorithm. And basically what we are doing here is some kind of lattice homomorphism techniques here. You don't need to know what these techniques are, but imagine that you have some many public matrices. There is some homomorphic evaluation procedure, which is outputting this short public key. And the way this homomorphic evaluation procedure looks is like, if you have an OR gate, then I'm going to basically add my matrices up. And if you have an AND gate, I'll maybe do some multiplication of these gates, but to make these dimensions work together, I'll maybe multiply by some G's. Now, if you have a very complicated circuit, then you can sort of combine these objects to produce the short public key. And the way these objects look is like, instead of computing on these inputs, now you're computing sort of these meta circuits on these attributes, on these public matrices. And the point here is that if the circuit that you started with, if that was width preserving, then this whole procedure, this whole setup procedure is also preserving the topology of the circuit, and it will also be width preserving. We will blow up by polylambda, but polylambda is fine. Okay, so then I have some open questions, but because I'm running out of time, I'll quickly speed through this. So improving the dependence on space is a big open question. And there's some follow-up work which does this, but they do need a new falsifiable assumption to do this. Can we come up with a more direct solution for better efficiency without bootstrapping this setup again and again? And we have another result in our paper, which we can get independent in time, but we undergo through a huge security loss. Again, AMR 25 do answer this question, but they do it from a stronger assumption. So yeah, that's it from me. Thank you.
Cool, thank you, Rachit. So I think we have time for 1 or 2 questions, and this is the very end of the session. It's 11:45. Does anybody have any questions? Okay, cool. I guess like this is actually the one we're gonna end right on time. So everyone can thank Rachit again.